Hello, bonjour, zdravo, Yorana. Welcome to the 5th tutorial of Statistical Mechanics, Algorithms and Computations from the Physics Department of École normale supérieure. In this week's lecture, we made our first move into quantum mechanics and quantum statistical mechanics. We use two languages. The first language is the one of wave functions and of quantized energy levels, both solution of the Schrödinger equation. For the harmonic potential, this is what we studied in harmonic wave functions.py. Besides this traditional approach to quantum mechanics, we also employed the language of density matrices. This led us directly to matrix squaring, to the Feynman path integral, and to path integral Monte Carlo simulations. To make the connection between wave functions on the one hand and path integrals on the other, we must provide the missing link, the density matrix at small beta that holds the paths together. This is like a spring constant of our quantum mechanical elastic object. We will arrive at this connection between Schrödinger and Feynman in two steps. First, in what follows, Michael will actually compute the density matrix for a free particle and derive and illustrate a result that was already presented in the lecture. He will then extend the simplest of all calculations using the path integral representation. Then Alberto will derive and explain the Trotter decomposition. Remember, among the three properties of the density matrix, this was the one which allowed to incorporate arbitrary interactions at high temperature. This simulation knows about the free density matrix and the Trotter decomposition, but not about much else, and certainly not about the solutions of the Schrödinger equation. So now, in these simulations, let us spend a moment to speak about the axis. In the wave function picture, the actions are the position x and the energy level E. So things are clear. But in the path integral picture, the axis here is again x, the position, but the y-axis refers to an inverse temperature-like variable tau. In quantum statistical mechanics, we call this variable the imaginary time. And this mysterious name adds to the fascination of path integrals. Vivian, in the last part of this tutorial, will tell us about the relationship between temperature and time. He will convince us that the Trotter decomposition at high temperatures can also be used at small times. This will allow you to simulate time evolution on the computer and to see some of the amazing effects of quantum physics, like the quantum tunneling effect. But now, let us listen to Michael explain to us the whence and the whither of the free density matrix and how it combines with the language of path integrals.
As Werner mentioned in this week's lecture, we are able to explicitly write down the density matrix of a particle in an arbitrary potential V. We do this by use of the Trotter decomposition formula. Unfortunately though, this approach is limited to the high temperature regime. On the contrary, for a free particle, that is the case v equal to 0, we're actually able to calculate an exact result which is valid at any temperature. So let us see how this is done. As in this week's lecture, we consider the Schrödinger equation. And in the case of a free particle, it reduces to the expression shown here. This is simply a wave equation, and you can easily convince yourself that it is satisfied by any sine or cosine wave, as sine and cosine simply reproduce themselves in the second derivative up to a sine and a scaling factor. When we put the particle into a box of size L, say by periodic boundary conditions, then we can only use sine or cosine waves whose period is equal to the box length L. Other waves simply don't fit. A complete set of waves that do fit is shown here, where the superscripts denote symmetric and antisymmetric wave functions with respect to the center of the interval from 0 to L. You see one ground state and a symmetric and an antisymmetric solution for each excited state with the energies En equals to 2 pi squared n squared over L squared. In Python, this gives the following program. It is analogous to the program harmonic wave function.py that was introduced by Werner in this week's lecture, and it computes the density matrix by summing over all states. So let us have a look at the density matrix by simply plotting the results of our little program. The stripe in the diagonal of the matrix indicates that the density matrix rho free of x, x prime and beta is in fact a function of x minus x prime only. This means that rho free is translation invariant, as the individual values of x and x prime do not matter, and only their distance, x minus x prime, counts. Rho free is largest on the diagonal. In fact, at high temperature, that is small beta, it is all concentrated on the diagonal where x equals x prime. As we lower the temperature, we see that the off-diagonal parts become larger and larger with increasing beta. This is a famous quantum coherence that is governed by the thermal de Broglie wavelength. Now let us do a small calculation. But for simplicity, we will not use the sines and cosines, but rather the equivalent complex exponential wave functions. You can actually check this equivalence by writing a small Python program. When you compare the output of this program to the output of the previous program, you will see that it arrives exactly at the same results as before. However, we promised an exact expression for the free density matrix, so let us now calculate it. Using the complex exponential wave functions, the density matrix is given by this expression, where you notice that each term is in fact a complex number. At first glance, this seems a bit strange, as we know that the final result will be real. This is because for each complex number in the sum, there is a complex conjugate counterpart, and together they become real. Having the particle in a box of size L is no true limitation, as we can let L go to infinity and replace the sum over n by an integral. This may sound difficult, but it can be easily understood when we introduce a dummy parameter delta n equal to 1, the difference between two successive n values. We then change the variables from n to lambda with lambda equals to 2 pi n over L. Thus we have delta lambda equal to 2 pi delta n over L. This leads to this term-by-term equivalent sum, where we use this result, which follows when we take c tilde equals to c over sigma squared from the Gaussian integral. This Gaussian integral was already evaluated in lecture 4, last week's lecture. We finally arrive at the free density matrix, where we have reinserted Planck's constant h bar and the particle mass m. The free density matrix is indeed a function of x minus x prime, and see how at large temperatures, that is small beta, rho free becomes infinitely peaked at the diagonal x equal to x prime, as we noticed earlier. Note in particular that the density matrix is positive, not only on the diagonal, but everywhere. For us Monte Carlo specialists, this is important, as you can interpret the density matrix as a probability. Now, in this calculation, we made a transformation from a sum to an integral when taking the limit L to infinity. But what is the density matrix of a finite box with periodic boundary conditions, that is, for finite L? The above sum can be evaluated using the famous Poisson sum rule, and the result is really simple. The parameter W is called the winding number, and you will see in a moment where this name comes from. The density matrix ρ of x, x prime and beta is made up of all the paths in Feynman's path integral picture that go from x to x prime directly, plus all the paths that wind around the box once. That is, they have the winding number W equal to 1, plus all the paths that wind around the box twice, and so on for higher winding numbers. Of course, we can also wind up paths to the left corresponding to negative winding numbers. This concept of winding numbers will come in handy 2 weeks from now. It is key to understand Bose-Einstein condensation. So we have now obtained the free density matrix at all temperatures, and it is a Gaussian of x minus x prime with a normalization 1 over the square root of 2 pi beta and a variance of square root beta. Next, Alberto will determine a general expression for all potentials at high temperatures using the Trotter formula. But before you go on, please take a moment or 3 to download, run and modify the programs discussed in this section. On the Coursera website, you will find the program free periodic sine cosine.py and its cousin free periodic complex exp.py. Take these problems apart to understand the inner workings of complex arithmetic that lead to a final real-valued and positive result.
As explained by Michael, for a free particle we can compute exactly the density matrix. This is of great importance, as we can compute the general density matrix, so to speak, which grows from this seed, as we will discuss. For what follows, you must understand that ρ x, x prime, beta is a matrix of 2 indices, x and x prime, but is also an operator, exponential of minus beta h. The matrix elements of the Hamiltonian H can be written in an arbitrary basis, and in this basis the matrix elements of ρ writes like this. This expression can be familiar for those of you who have studied a little bit of quantum mechanics. But for all of you, please retain that the density matrix is an operator. The exponential of minus beta h is the direct generalization of the Boltzmann distribution. Let us now consider the density matrix of a system with the following Hamiltonian: H equal to H3 plus V, where H3 is the Hamiltonian discussed by Michael, and V is the interacting potential that for the harmonic oscillator is 1/2 x squared. Now, the Trotter decomposition corresponds to the following expression. To see that this is true, we will expand both terms up to the order beta square. But attention, H3 and V are operators. The product VH3 can be different from H3V. Operators, matrices, in general do not commute. So let's start from the second term of this equation. We can first expand exponential minus beta over 2 v of x. A corresponds to the linear term in beta and B to the second order term. Then we expand rho free. C is the linear term and D is the second order term. Finally, we can also expand exponential minus beta over 2 Vx prime. So let's reorganize these terms order by order in beta. At the zero order we have 1. At the first order in beta we have A plus C plus E. And then we need a little bit of work to write the second order term. This expression fully agrees with the direct expansion of the full density matrix. These two equations prove that the Trotter expansion is correct up to beta square. Please note that these manipulations are valid on operators and wave functions in a finite box. In Python, we can implement the Trotter decomposition using Michael approach and plot the entire density matrix at high temperature. Remember, the free density matrix rho free x, x prime, beta is a function of x minus x prime, and this gives the nice stripe in this diagram. Now let us add the harmonic potential V to the Trotter decomposition. You see that for large x and x prime, the density matrix is suppressed, and this is what keeps close to the origin the quantum harmonic oscillation. In this week's homework, you will use both the Trotter decomposition and the convolution properties to compute the density matrix up to very low temperature. As you must square the matrix many times, the approximation errors will grow. However, the quality of this approximation, correct up to beta square, is so high that it will survive up to low temperature. The Trotter breakup is completely general. It applies to an arbitrary potential and, as will be shown by Vivien in a moment, can be even turned around to describe the real time evolution of the system. But before understanding why the inverse temperature beta is an imaginary time, please take a moment to download, run and modify the program harmonic trotter movie.py, which implements the Trotter decomposition and provides a nice graphical output. You can check this approximation, and actually in this week homework you will test this approximation against the output of harmonic wave functions.py.
In this section, we examine a complementary problem, which is the time evolution of a quantum system. Werner Michael and Alberto have explained to you in the previous sequences how to describe a quantum system at finite temperature in equilibrium by the use of the density matrix. However, in general, systems are described by a wave function psi of t, which evolves in time. So, if we fix this wave function psi of t equals 0 to be equal to psi 0 at initial time, it evolves in time according to the Schrödinger equation displayed here, which is I times the psi over dt is equal to h times psi, and here h is the Hamiltonian of the system, and we have also fixed the constant h bar to be equal to 1. To solve this equation, one may be tempted to replace the time derivative by a first-order approximation, which is displayed there, but this is not an option in our case because this would break the conservation of probability. A better choice is to consider the operator solution of this equation, which writes as follows. It is psi of t is equal to e to the power minus I h t times the initial vector psi of 0. You may indeed check by differentiating with respect to t that this expression is the solution of the Schrödinger equation with initial condition psi of t equals 0 is equal to psi 0. Now let's have a closer look to this formula. You note that by formally replacing I times t by beta, that is to say by working in imaginary time, you obtain the very same expression as that of the density matrix that we know for a quantum system at equilibrium at inverse temperature beta. So this relation provides us a dictionary, a mathematical dictionary between time evolution and thermal equilibrium. It is not only beautiful from an abstract point of view, but also very useful in practice. Indeed, you can apply what Alberto has told you about the Trotter expansion to devise an algorithm which allows you to study very efficiently the evolution of quantum systems. Let us now focus our attention to a particle of position x in a potential v of x in dimension 1. If we set the mass of the particle to be m equals 1, its evolution is governed by the Schrödinger equation of Hamiltonian h is equal to h3 plus v of x. The idea is to decompose the full time interval t into n steps, time steps of duration delta t is equal to t over n. The full operator of evolution is now expressed exactly as a product of n infinitesimal operator of evolution as displayed here. Each of these infinitesimal operator of evolution writes as e to the power minus I times delta t times h. Now, to understand the contribution of the two components h3 and v of x of this Hamiltonian, we can use Alberto's Trotter decomposition, which writes as follows. You recognize the same formula where beta has been replaced by I times delta t. This approximation is valid up to order delta t to the power 2, that is to say, the first error term is of order delta t to the power 3. Let us examine each term of this product. The first and the last term are easy to understand. They consist in the multiplication by the same factor e to the power minus I over 2 times delta t times v of x. the free term is a bit enigmatic, but the mystery is lifted by transforming the wave function to Fourier space for the spatial coordinate. This consists in going from the real space psi of x and t to the momentum space psi hat of p and t. You will easily convince yourself, for instance by reading the short fact sheet associated to this tutorial 5, that the action of the free operator consists in a multiplication by a factor e to the power minus I over 2 times p squared. So, the action of this operator is just the multiplication by a Gaussian factor. This provides a possible scheme to devise an algorithm, which is the following. First, define the initial wave function, then discretize the time interval t into n time slices of duration delta t, define the Fourier procedure, and apply the Trotter formula many times. At each time step, first, in real space, multiply by a factor e to the power minus I over 2 times delta t times v of x, make a Fourier transformation, multiply by e to the power minus I over 2 times p squared times delta t, and go back to the real space, multiply by the same factor as previously. This is the only steps. You just have to iterate, and this gives the following beautiful algorithm: quantum time evolution.pi. This method is really powerful. To illustrate it, let's consider the fate of a quantum particle confined between two barriers, an infinite barrier on its left and a finite barrier on its right. The particle starts from some position between the two walls. If the particle were classical, it would bounce forever between the two walls. You observe that each time the wave function bounces on the wall on the right, a finite but tangible proportion of the wave function actually goes through the wall. This quantum tunneling effect is a genuine quantum effect and has no classical counterpart. We have illustrated how our mathematical dictionary between real time and imaginary time has allowed us to observe the quantum tunneling effect in a simple one-dimensional situation. However, have in mind that the very same effect has deep physical consequences from, for instance, the radioactive decay to the construction of the transistors in the CPUs of your computer, or, in more complex situations, to the device of the scanning tunneling microscopes, or even to the evaporation of black holes. It is now time for you to download, run, and modify the beautiful program we have seen in this section, quantum time evolution.pi. Check it out. See by yourself how a quantum particle can tunnel through a wall and program maybe some other exciting potentials. Take also a look to the fact sheet, which explains to you how the Fourier transform from x to p is implemented in practice.
In this tutorial, we zoomed in to the density matrix and its three main properties: the convolution, the free density matrix, and the Trotter decomposition. We already perceive the plot of these three stage characters that prepare for a great story and that will lead us to quite complicated situations. In what Alberto and Michael told us, the density matrix remained positive and real, allowing us to interpret it as a probability and to do quantum Monte Carlo. This positivity is preserved for many particles, arbitrary interactions, and even for bosons. It is broken in the case of fermion Nick particles. In what Vivian told us, in the time evolution, all of this was broken also. The density matrix was complex valued and it could be negative. The great algorithm produced only works in one dimension because quantum time evolution is a really hard nut to crack. So now it is time for you to look at how these three characters that we described intervene in practice. And we wish you good luck and a lot of fun with the homework session 5.